all we've learned now about meteorology and you're going to do a forecast. Well, in order to do a forecast, you got to have some things. One of them is you got to know what's going on in the weather right now. We've talked a lot about what is weather. And weather is the here, now, what's happening outside your window or around you at this instant in time. So first thing we're going to try to do is come up with, what is that? Well, if I'm looking at a forecast, let's face it, the weather moves. So I need to know what the weather is here and now over a pretty large area. And this actually does involve international cooperation. We have aircraft that actually transmit winds, temperature, moisture from where they are. We have polar orbiting satellites. We have GOES, geostationary satellites. We have ground stations that take all this data. We have upper air balloons. We have surface observations. We have some buoys in the ocean. We even have ships. Some ships take observations. But still, does it really tell you the entire picture of what's going on? We can look at this. All of this data is put into current observations, which every forecast office in the U.S. gets. And we can cut those down into segments that particularly look at our office. This is a very similar office to what I worked in. Buoys out over the bay, not nearly enough of them. There's cooperative observer programs. These fill in some of the gaps, but they only report maybe once a day or maybe once a month. So the information is not exactly real time. Radiosondes, wonderful tool, gives you some really good information on the vertical structure of the atmosphere. Look at how few of them there are. Not exactly a lot, is there? All of this comes into a tool we call the AWIPS, Advanced Weather Interactive Processing System. I got to play with that a lot, programmed it some, and AWIPS 2 is the current version of it. And combined all that, now that we've just got these observations, we're going to make a forecast. We want to know what the weather is going to be a few hours out, maybe, or maybe a couple days or a week, even more out. And everything we have talked about, I haven't really showed you the government primitive equations, they're called, for the weather. The reason is they're all calculus, they're all complex, and we can't solve them. No mathematician has ever been able to solve the type of equations we have. So everything we do is an approximation. You learned about the hydrostatic assumption, hydrostatic equation, and air being in equilibrium. Well, guess what? That's wonderful if you don't have a thunderstorm. We talked about air moving at a steady pace. Well, if you have a thunderstorm, air is not moving at a steady pace. It's accelerating up and it's accelerating down. So we just threw out the hydrostatic equation as we know it. And we have to add a whole bunch of other terms to that, which are kind of unsolvable. So these are some of the basic models that we use. HRRR is one we use for high resolution. NAM is North American model. Mesoscale model, again, a fairly high resolution model. Global forecast system, look at the entire globe. And then there's coupled, where we actually couple the ocean and the atmosphere together in the global forecast system. And because we can't solve these models directly, what did we do? We decided to make ensembles of them. So what we have done is created a 6 hours over out to 16-day ensemble of the global forecast system. To make an ensemble, what we do is we know we can't solve the equations properly. We put approximations in there. Well, maybe we change those approximations to give one set of ensembles. Oh yeah, I talked about the analysis of what's going on. Well, we know that our analysis is not exact. So let's tweak that analysis. Let's try to find statistically where we might be most likely to be off and try to accent that area. And there are all kinds of high-level statistics that are done in that to help us give new analysis, which then can be put into the models and run. All of this gives ensembles. It gives short-range ensembles, and it gives high-range ensembles that look at the whole globe. Forecasts of tropical systems have taken a major improvement since we started using ensembles and brought in more data to them. Look at this. I mean, our error. We never used to make a 120-hour forecast, you can see, before 2000. Now, the 100-hour forecast is as good as what used to be a 48-hour forecast. That speaks a volume about how accurate we are in knowing what the hurricane is going to do. And we keep improving that. Yeah, some days are not as good as others, and some storms are not. But this is an average of all the tropical cyclones that occur. We are quite good. However, intensity, we stink. We're getting better, and we're getting tools that estimate when intensities might increase, but there's still something we're not good at. We also talk about where all the forecasts come from. In the National Weather Service, there's a National Center for Environmental Protection. Under that are broad areas of forecasting. So let's take a look maybe at some of that from this perspective. Here is the Weather Prediction Center, a branch of NCEP. You'll notice it comes out with these charts that have a 24-hour forecast of where things are. Here's tropical depression Nicole. Going through, this is valid at 7 p.m. this evening. And so it's coming up on the east side of the Appalachians, barely. They also issue precipitation and snowfall forecasts. So as you can see here, you got some pretty heavy precipitation coming up here, but not much in the way of snowfall. But you do see the blue area here. So some areas to the west of the storm are actually getting some light snow. They issue a 7-day forecast with maps and this information on it. So that is their job. Now, if I'm down right here making a forecast for Ohio, or one for West Virginia, or one for my area, there's a local forecast office that sees this and even talks to these people about why they're doing it. I have the right as the local forecast office to deviate from that or to adjust it some. Another part is Storm Prediction Center. The Storm Prediction Center right now has me in a tornado watch. Storm Prediction Center issues that watch. They issue it in coordination with the local forecast office. When I was working at the different forecast offices, they would call up and we would chat about whether we should or should not issue a watch. Most times, if they want it, they get it. I'll be honest. But there have been times I've convinced them to leave out part of areas or add in part of areas based on what we thought we're seeing at the local level that maybe they were looking at the national level and not seeing quite as closely. And they'll listen. So this is all related to severe weather here. And yeah, there's a threat at my house. And there's even, looking down here, potential for another watch, maybe issued 40 minutes ago. Then we have all these models, and this is just some of them. The Global Forecast System, ensembles, North American ensembles, North American mesoscale, high resolution mesoscale. Another one. And there's more. If I were to go over to tropical, you would have a whole different set of models. You can see all the different locations. Some are these, like the HRRR or the RAP. They update hourly, and they go out only about 18 hours. So you're really looking down at about a 2-kilometer area. Some of these other ones, GFS, more like 4 to 5 kilometer area, and looks at the whole globe. Here's another ensemble. We even have wave models that come out of all of this that can be used to forecast waves on the coast. So then again, looking, this is all part of NCEPT here. Aviation Weather Center is part of NCEPT. While it doesn't write the local terminal area forecast, the TAFs, it does write a broad, does broad systems and air mets and sigmets and all that. There's water. NCEPT also, underneath it, has some river forecast centers are local flood control, flood estimates. They take into account the local topography, the local runoff. But the National Weather Service Forecast Office actually issues flash flood warnings and river forecast warnings. And finally, down to the local forecast office. Here's my area, and I live in that square right there. That is the area that we forecast for. There's a bunch of those. You think about it, there's a grid here, all of these across the area. And that is what's used. We forecast temperature, we forecast pressure, we forecast precipitation probabilities. If you were to look at it, here's an hourly forecast for my house telling me, okay, here's my temperature. It's going to get up to about 74 or so, 77, 78 tomorrow. And then look at it, it's down in the 40s. Not what I like. You can see the wind speeds here. It gets a little breezy this evening out of the south. But then it shifts to the west during the day tomorrow, and you can see right here a cold front goes through. Notice my timing between 7 and 9 o'clock. These are hourly forecasts. So somewhere between 7 and 9, I have a cold front go through on Saturday night. And you can see at the same time the relative humidity went up in the evening, and then it starts plunging. Chances of rain are there. Better chances right now. And the total rainfall is here too. And even the chances for thunderstorms. Oh yeah, if there's a probability of snowfall, that's in there. Or sleet. And this is carried out for 7 days. The best forecast, the next 24 hours. Each day after that, we're not quite as good. So, hope you got a little bit out of all the complexity that went into this. How looking at the global picture, we reduce it down to the more local scale, finally to your house. So, hope you got something out of all that. Let me know if you have any questions.